Hi, it's time for another math easy solution. Today we're going to discuss further into differential equations and now look at predator-prey systems. And before I get to it, like always, you can download these exact notes in the video description below in the link there, and also subscribe via my email newsletter at mes.fm/subscribe. And also donate at mes.fm/donate if you like my videos. Anyway, so let's move forward. So predator-prey systems. So in my earlier videos, I went over a variety of models for the growth of a single species that lives alone in an environment. And you can see all those videos on population growth in the video links below. But now we consider more realistic models that take into account the interaction of two species in the same habitat. And we will see that these models take the form of a pair of linked differential equations. As opposed to just one, you have a pair now that are linked together. And we first consider the situation in which one species called the prey has an ample food supply, and the second species called the predators feeds on the prey. In other words, they eat the prey. So examples of prey and predator systems include rabbits and wolves in an isolated forest. Yeah, the wolves eat the rabbits, etc. Food fish and sharks. This food fish just fish being used as food by sharks. And amphids and ladybugs. I think that's how you pronounce aphids. Here's a good blog post from someone about them. So aphids are like plant lice. They basically, yeah, they eat plants and other stuff. And I just want to show this photo. Here's a cool photo of a ladybug eating some aphids or plant lice. It's pretty cool. So moving forward, so bacteria and amoebas, and amoebas, these are some sort another type of organism. Here's just a link here. And so they're often called amoeba. They're a cell organism that has the ability to alter its shape, etc. And I just took a quote from Wikipedia. The food sources of amoebae vary. Some amoebae are predatory and live by consuming bacteria and other protists. I'm not sure what those are. Some are dirtivores and eat dead organic materials, etc. You can learn more about that through that Wikipedia article. And so basically our model, before I get to that, so these are examples of prey and predator systems, and they arise in many different fields. And basically our model will have two dependent variables, and both are functions of time. So this is the kind of model we'll get to. So first thing, we can let R of t be the number of prey, and using R for rabbits. So we'll use the rabbits and wolves analogy to set up our formulation. And then W as a function of time be the number of predators with W for wolves at time t. So these are just the populations of rabbits and wolves, or prey and predator. So in the absence of predators, the ample food supply would support exponential growth of the prey, as I've gone over my earlier videos on exponential growth. So for the prey, the growth rate will be dr over dt, or the rate of growth. This equals to a constant, we'll call it k, times it by the population. Population of the rabbits or the prey. So, and again, this is just saying the growth rate is proportional to the population. And since it's growing, we're going to have k as just a positive constant known as the proportionality constant. So in the absence of prey, we assume that the predator population would decline at a rate proportional to itself. In other words, if there's no food to eat because it's eating the prey, it will just die off eventually. So we'll model that assuming there's no prey or no food supply, as the growth rate of the wolf population or the predator is equal to negative, and we'll use a constant r. So it's a negative rate and then proportional to its population size already. And again, where this constant r is a positive constant. So as you can see, the negative is just to enforce that it's declining in our model. So with both species present, however, if we have both of them, these are just with each other. So the prey grows because there's a lot of food, just grows, no one's attacking him. and then the predator dies off because there's nothing to eat. So with both species present, however, we assume that the principal cause of death among the prey, yeah, typo, not amount, is being eaten by a predator. So that's the only way we're going to assume, or the principal cause, or the main cause, that the prey is dying off, is they're getting eaten by the predator. In our case, wolves. So the birth and survival rates of the predators depend on their food supply, namely the prey. So yeah, if there's nothing to eat, you're just going to die off eventually. And yeah, so we also assume that the two species encounter each other at a rate that is proportional to both populations, and is therefore proportional to the product of the wolf and the rabbit population, RW, or the prey and predator. Yeah, basically the more there are of either population, the more encounters there are likely to be, and vice versa if there's less. So we're going to assume that that the encounter rate is basically proportional to the populations multiplied by each other. Yeah, so with that assumption and with these other assumptions, a system of two differential equations that incorporates all of these assumptions would be: the first one for the prey, dr over dt equals to its exponential rate model, kr, but then we have to subtract, and we'll add another proportionality constant, a, and this is multiplied by the rw. In other words, it's so the growth rate of the rabbit population or the prey is decreasing. Yeah, it's decreasing based on this factor that's resembling the encounter rate with the wolves or the predator, but it's increasing just naturally here from its own food supply. So you have this type of model, but then you're interlinked with another model for the growth rate, so dw over dt. So this one, they're dying off because there's no food, so you account for this one minus rw, but then when there is food, we're going to say plus b times rw, or the encounter rate. Yeah, so it's increasing population based on the encounter rate, or how often it sees its prey, yeah, or how often the wolves see the rabbits or encounter them, etc. Yeah, and where k, r, a, and b are all just positive constants in this model. So notice that the term minus r, negative a, r, w decreases the natural growth rate of the prey, as I stated, and the term b, r, w increases the natural growth rate of the predators. And these equations are known as the predator-prey equations, or the Lotka-Volterra equations, and I'll go over a brief history on these guys in a bit. And a solution of this system of equations is a pair of functions r of t and w of t that describe the populations of prey and predator as functions of time. So that the solutions are yet two functions. And because the system is coupled, meaning that r and w occur in both equations, so you have r and w in this equation, you have r and w in both of them. Yeah, we can't solve one equation then the other. So if you solve one, it affects the other. So you can't do that. You have to solve them both simultaneously. And unfortunately, it's usually impossible to find explicit formulas for r and w as functions of time. But we can, however, use graphical methods to analyze the equations. And I'll go over examples in later videos, so stay tuned for that. Yeah, and now let's just go over a brief history on these equations as well as the founders behind it. And yeah, and I do this quite often whenever I introduce a new topic or a new equation, and if there's some interesting history behind it, I usually go over a brief history just for your reference. So this is from a calculus book. The Lotka-Volterra equations were proposed as a model to explain the variations in the shark and food fish populations in the Adriatic Sea by the Italian mathematician Vito Volterra, born 1860-1940. And just for your reference, Adriatic Sea, where it is in the world map, it's over there, just above South Africa, and it's in Europe. And then you click a closer look, and as you could see, it's just above Italy, below Croatia, Slovenia, etc. So that's the Adriatic Sea. And through the Wikipedia page here on the equations, I just copied a pretty interesting bit of history from it, put it here. So the Lotka, let's make a space. See, the Lotka-Volterra predator-prey model was initially proposed by Alfred Lotka in the theory of autocatalytic chemical reactions in 1910. You can learn more about those. Yeah, it's hard to pronounce for me. Anyway, so this was effectively the logistic equation, and you can learn more about that in my video link below. But then in 1925, he utilized the equations to analyze predator and prey interactions in his book on biomathematics. So initially, he was doing that to model predator prey, but it was pretty much a logistic equation, and eventually formulated what's now known as these predator prey equations. And then, but this was 1925. But what's interesting is these same set of equations were published in 1926 by Vito Volterra, a mathematician and physicist who had become interested in mathematical biology. Volterra's inquiry was inspired through his interactions with the marine biologist Umberto d'Ancona, who was courting his daughter at the time, was later to become his son-in-law. Yeah, it's pretty interesting. And then d'Ancona studied the fish catches in the Adriatic Sea and had noticed that the percentage of predatory fish caught, these are fish that eat other fish, had increased during the years of World War I, 1914, 1918. And this puzzled him as the fishing effort had very much reduced during the war years. So yeah, this is interesting. Yeah, so there's less of these predatory fish as a percentage, and they were fishing less. And Volterra developed his model independently from Lotka, so that's interesting, independently around the same time, and used it to explain d'Ancona's observation. And basically how you fish, when you fish, that it will affect the predator-prey populations and their growths and they're both interconnected. And that's pretty interesting. So they did it both independently. And some, if you go to the wiki page of Alfred Lotka, you could learn more about him. So just a brief bio on him: Alfred James Lotka, born March 2nd, 1880 to December 5th, 1949, was a U.S. mathematician, physical chemist, and statistician, famous for his work in population dynamics and energetics. An American biophysicist best known for his proposal of the predator-prey model, developed simultaneously but independently of Vito Volterra. And the Lotka-Volterra model is still the basis of many models used in analysis of population dynamics in ecology. And also, lastly, we'll go over Vito Volterra's. Here's a link to it just for your reference. That's how it looks like. And basically, Vito Volterra, born May 3rd, 1860 to October 11, 1940, was an Italian mathematician and physicist known for his contributions to mathematical biology and integral equations, and being one of the founders of functional analysis. And born in Ancona, then part of the Papal States, or the states or countries or territories owned by, pretty much run by the Pope, into a very poor Jewish family. Volterra showed early promise in mathematics before attending the University of Pisa, where he fell under the influence of Enrico Betti, and where he became professor of rational mechanics in 1883. So there's another interesting fact about him. In 1922, he joined the opposition of the fascist regime of Benito Mussolini, and in 1931, he was one of only 12 out of 1,250 professors who refused to take a mandatory oath of loyalty. That's quite remarkable. His political philosophy can be seen from a postcard he sent in the 1930s, on which he wrote what can be seen as an epitaph for Mussolini's Italy. Empires die, but Euclid's theorems keep their youth forever. That's quite interesting. There should be a quotation over it. However, Volterra was no radical firebrand. He might have been equally appalled if the leftist opposition to Mussolini had come to power, since he was a lifelong royalist and nationalist. As a result of his refusal to sign the oath of the allegiance to the fascist government, he was compelled to resign his university post and his membership of scientific academies, and during the following years he lived largely abroad, returning to Rome just before his death. That is quite remarkable, and this is a quite fascinating statistic here. He would not take the oath of loyalty, or the mandatory oath of loyalty, which is quite remarkable. And this is 12 out of 150. That's unreal. Anyways, that's all for today. Hopefully you'll learn. Hopefully you'll enjoy this just brief history on Lotka and Volterra and these predator-prey equations. In later videos, we'll go over some examples illustrating how to solve these or graphically represent them. Anyways, that's all for today. Like always, you can download these exact notes in the link below. And thanks for watching. Stay tuned for another Math Easy solution.